Bismillahirrahmanirrahim. Let's continue. So probably the sixth 1.6, the sixth section will be in a separate lecture, so in separate video, because the previous section took about 40 minutes. So there will be, but it's okay. We try not to exceed 1 hour for each lecture, between 40 minutes to 1 hour for each lecture. More than 1 hour, it will be really hard to follow. So other methods. So this will be probably I have not yet finished filming, but this will be probably the fifth lecture and the last section. So we have seen Abou Kamel method in detail. We have seen its pros and cons and edge cases in the previous section. Now let's have a look on the other methods. As I said in the introduction, there are two big types of methods. The bracketing method. Let's check. Yes, okay. The bracketing T methods that bracketed the solution will always converge, and open methods that might diverge, go far from, in some cases, they can diverge. This is the main disadvantage of open methods. In bracketing methods, we have seen Abou Kamel methods, Abou Kamel's method, and we have seen also its a slight modification by Snyder, the Illinois method, the Illinois modification. It's not a new method. Some people call it the Illinois method. It's not the Illinois method. It's Abou Kamel's method, but with a slight modification. And the bisection or dichotomy method. Dichotomy method. This is the easiest, the simplest technique is the dichotomy or bisection method. That is slow. We see it right now. In open methods, we have Newton methods, also called Newton-Raphson method. This is the fastest method, but it has drawbacks also, important drawbacks. And the secant method. The secant method is based on Newton method, so a slight modification to Newton-Raphson method. And finally, the fixed point method. So we have already studied that in detail. It's the main method for our topic. I will review this fourth method right now, but briefly, of course. See the method graphically. We see the formula, how to obtain the next point, how to progress to the solution, and some advantage, disadvantage of the method. So let's start with the dichotomy method. Dichotomy method, also called bisection method. So let's draw the axis. Let's choose an interval, and let's draw the curve of our function representing the equation. This is the exact solution. This is the images of the endpoints, and this is our interval, our first interval, our input. So the method, what it did, it subdivide the segment into it, bisect it. So let's say we have 4 and 4. Let's say this is the first approximation to the root. Then we have left or right. In this case, at the left. It's a bracketing method. The sequence of XR or XRI are always between A and B. So at the right or at the left, then subdivide it in two. Bisection means, or dichotomy means subdivide in two. So we have two intervals exactly having the same length. It's in the middle. XR2 is in the middle of the interval number 2. And then again, at the right or at the left, at the right. Here it oscillates. This method frequently oscillates. And then in the middle, and then at the right, and then in the middle, and so on. So its formula is XRI plus 1, or XRI, I mean, not plus 1, XRI, the current position of the force point, or the approximate point, is the lower, XL, plus the upper of the current interval, over 2. It's in the middle, why, and so on. So this is the formula. It's very easy, very simple, and you can observe here, there is no image. The image, the curve, the function, has absolutely no influence on the sequence of, so this is the first thing to observe. The function f has no influence on the element of the sequence. It is also a bracketing method, so it always converges. It is a bracketing method. And finally, because there is no information on the curve in the element of the sequence, the method could be slow. In some cases, it could be really slow. So the method is generally slow compared to Abou Kamel. The method is generally slow. And finally, we can observe also that it often oscillates its interval. In contrast with the Abou Kamel method, as we have seen in general, in most cases, it does not. If it catches the root at the right, the subsequent intervals will be also at the right, and the same if it was at the left. There are special cases, as we have seen in the edge case section. There are when the root is an inflection point, then you could expect there, even in that case, there are cases, even when it's an inflection point, there is no oscillation. So it really seldom when it oscillates. So it often oscillates its interval. That's it for the dichotomy method. We will not see an application or an algorithm, just an overview. So let's see the Newton-Raphson method. This is also a very important method, but it has also important pitfalls. So the method is based on the derivative of the function. So we need not only to evaluate the function at each iteration, but also the derivative. Let's draw the axis, and let's see the method through an example. And let's draw it like this. And this is the curve. First thing first, the method doesn't need an interval, actually. Open methods don't need an interval. You can provide an interval, of course, but you should provide for the Newton-Raphson method a start point. This start point can be any point in the interval containing the solution, but the interval itself is not mandatory. So let's take a point here, relatively close to the solution, and call it x0. The indices will be here, not upper. Will be here. So let's write it. And this is the image of x0. But it's not only the image we need the derivative to draw the tangent. So tangent will be like this. This is the tangent that is f prime 0. F prime 0 means the derivative of f at x0. That's the meaning of. So it's the tangent of this line. I mean the slope of this line. This line is the tangent to the curve at this point. The image of x0, f0. f0 is the image of x0. And this is the intersection. The intersection of the tangent with the x-axis is our new approximation, x1. And we repeat the process again. The image is here, and the tangent at the image of x1 will be here. Something like this. So it's very close. It converges very fast. This is the fastest method in this topic, actually. So, but it doesn't make it the best method, because there are other things to consider. So this is f1, and this is the tangent, the derivative f prime. The tangent is defined by the derivative. The slope of the tangent is the derivative. It's a well-known thing in the calculus. So this is x2. And we can write the method in general. The formula, the next point equals the current point minus fi, the image of xi, over its tangent, with the condition that the tangent at the point I is different from 0. Otherwise, the method will not work. If the derivative equals 0, means the tangent is parallel to the x-axis. So if you get a point where the tangent is parallel to the x-axis, the next point is undefined. And this is the divergence. It diverges. So this is the formula. How we get this formula? We can get it by reasoning graphically on this triangle, the tangent and the x-axis, or using Taylor's series. I better will not go in details. I just give an overview of the method. So the first thing to observe here that in the input, we need both f and f prime. And this is a disadvantage because you have to calculate the derivative and you have also to evaluate it at each iteration. So the second disadvantage is that you have to calculate at each iteration, you have to evaluate two functions, not one, like in Abou Kamel. Two functions, f of x, I, and its derivative, f. So not only you have to provide the function f prime, which is not a big deal in majority of cases, but there are cases where you don't know the function analytically. There are cases in practice you don't have the function itself. As we will see that later in another chapter, interpolation. You know the function only in a finite number of points, and then you interpolate the function in the other points. So we don't have any way to calculate the derivative. So yeah, at each iteration, evaluate two functions, the function that represents the equation and its derivative. And finally, a good point for this method is it's very fast. Very fast. How fast it is? What does it mean very fast? We will see that later on in this section. We can say now that its order of convergence is quadratic. What does that mean? We'll see that later. So here we write just it's very fast method. It might also diverge. Let's see an example of divergence quickly. It depends of the function, of course, of the curve of the function. So let's take an example that shows us how the function might diverge. Let us take x0 here, the start point. Its image. Let's draw the tangent. Should be here. Cuts the axis here. Its image. Its tangent. As you can see, it gives very far points, and here, if the curve, for example, will be like this. The image will be here, and the tangent will be completely different, and the method diverge. Of course, it goes far from the solution we are interested in. So this is x0, this is x1, this is x2, this is x3, and so on. This is a divergence. Here it converges, but here it diverges. When the method converges, it's the fastest. But there are many cases where it can diverge. This is the main disadvantage of the method. So let's write it here. It is very fast when it converges. And there are many cases where the method diverges. So this is an overview of the Newton-Raphson method. I explained it graphically and give the formula of the sequence that tends to the root. And this is the main disadvantage of the Newton-Raphson method. But that's why I didn't choose it for this topic as our main method. The third point is the secant method. Is based on Newton-Raphson method. It replaces the derivative f prime, it replaces it by an approximation. So we try to avoid the main disadvantage, one of the main disadvantage of the Newton-Raphson method. The Newton-Raphson method has two disadvantages. It needs the derivative, and it might diverge. The secant method also diverges, can diverges. All the open methods can diverge, I mean. But it proposed to change the derivative with an approximation. Fi minus 1, the image of the current and the previous point, over xi minus 1. So the tangent is replaced by the relative variation of the image with respect to the distance between the 2 points. And this leads to the formula xi plus 1. The next point is fi xi minus 1 minus fi minus 1 xi over fi minus 1, which looks like Abou Kamel, but is different. It's not Abou Kamel method. It's not a bracketing method, as we will see that graphically. But let us first note fi means the image of xi, and fi minus 1 means the image of xi minus 1, for the definition of the notation. And it needs two start points. It needs not one start point as the Newton-Raphson method. It needs 2 start points. Any start points close to the solution. We can also take them as the end points of the interval, bracketing the solution. We can also do that, but it's not a bracketing method. So let's see that through an example. Quickly, the axis. the x-axis, the y-axis, and let's try our function. Let's draw our curve of our function like this. Like this. This is the curve. As I said, we can take x0 here, the lower bound, and x1 here, the upper bound. And the secant method, it joins the images. It's a chord also, like Abou Kamel, it's a chord that joins the images of f1 and f0. And the intersection is the next point, x2. And we repeat the image here. No lower and upper interval, left and right interval. No interval here. It just works with the current and the previous point. So the current point now is x2, the previous is x1. So it joins their images. This is f2, this is f1. And the second chord. We get x3. This is x3. And this is its image. And the chord joining the images, the current image and the previous image. And as you can see here, it differs. The first iteration it looks like Abou Kamel, but actually it's not. This is the solution. And we can see here, it goes like this. Oh, this is x4. And then we have the point here, the image. The images are always carried by the curve. And again, we join the current image, the image of the current point, and the image of the previous point. So it works with the current and the previous, no interval here. It's not a bracketing method again. So it must cut here somewhere here. So it converges fast. It is faster than Abou Kamel's method without the modification of Illinois. And it is slower than Newton-Raphson. It's between. But unfortunately, it also might diverge. So this is the secant method. Now let's note it here. The method is slower than, let's note it, Newton-Raphson method, but faster than Abou Kamel method. And its main purpose is not to use the derivative. So, like Abou Kamel method, at each iteration, the cost of iteration, at each iteration, it evaluates only fx, not the derivative. So this is the secant method. Let's move to the last one, the fixed point method. So the fixed point method, it makes a slight change to our equation. Our equation is fx equals 0. Find x becomes gx equal x. Find x. With g, x is actually fx plus x. Graphically, what does that mean? It means the following. So let's see the method graphically, how it works. Oh, this is the x-axis, and this is the y-axis. And let's draw our curve like that. This is the curve of G. This is the curve of G, not of F. We are interested to solve this modified equation. It's the intersection of G graphically, not with the x-axis, but with the bisector, which is this line cutting the angle in two. It will be like this. This is the solution of this equation, and equivalently of this equation. So we transform the problem to the intersection of the curve G, with the bisector. This is called the bisector. Bisector. How we do that? We start also with a given point. For example, this one. For example, this one, close to this one. This is x0. I mean, not this one xr. I beg your pardon. This is xr. It's the abscissa of this point. This is the unknown. So what we do, we start with a point. It needs also a start point. And we look for its image. The formula is that the next point is equal the image of the current point. So we look for the image of x0. It is carried by G. By G. This is the image. This is G0. But because of the bisector, this is also the image. So G0 and this point are the same. Because of the bisector, they are like a symmetry, like a mirror. Is 0, and this should be x1. x1 is equal to G0. This is what the formula tells me. The next point is the image of the current point. How we do that? We move to the curve, and then we move to the bisector. We move to the curve to get G1, and then we move to the bisector to get x2, and then we move to the curve, and then we move to the bisector, and so on. So let's write it here. This is G0, this is G1, this is G2, and so on. And this point will be close to this point that gives us the solution. This is the idea of the fixed point method. There is another model. This goes like this. There is another model. Quickly, let's show it. This method also diverges, unfortunately, as I said. All the open methods might diverge depending of the curve of the equation. So let's use one single color because of time. Okay, should be like this. Bisector, and again the curve of G, not of F, like this. This is the bisector, and this is the curve of G. We have a start point here. This is intersection. This should be our root. So what we do, we start with a point, x is 0. We go to the curve. From the curve, we go to the bisector. From the bisector, we go to the curve. From the curve, we go to the bisector, and so on. And it's like a spiral. And so on. We have this point, this point, this point. And they oscillate on these two sides of the curve G. So this is for the fixed point method. It needs, this is its formula, and it needs a start point where we begin with, not an interval as an input. And I think that's it for the overview. But there is two other points important to conclude and finish this chapter. So, fifth point is notes and conclusions. Notes and conclusion of what we have seen so far. So when we compare the method, we need two things. When we contrast methods, either in this topic or any other topic, we need two things. We need performance of each iteration, and the cost of each iteration. Like, for example, Newton method, let's say it takes 3 iterations to the root, to the exact root. So first, second, third. So first, second, and third. While Abou Kamel, it takes 6 iterations. But see the cost. Here it needs 2 evaluations of a function, the function and its derivative, which are the most expensive operation per iteration. But here, Abou Kamel method, it goes like this: first, second, third, fourth, fifth, sixth. So it might take a number of iterations greater than Newton method, but each iteration is faster, is twice faster at least than the Newton method. So we have to consider both the performance of each iteration and the cost of each iteration. What is the performance of it? What does it mean? It means in our case, it means the absolute error, how much it drops. So performance is measured by how far or how big the error, the absolute error at each iteration drops. In Newton-Raphson method, we can show analytically using Taylor series that the next error, the absolute value of the next error, is of the order of EI square. Now, what does that mean? Means, for example, at the first iteration, we have an error of 0, 0, 1. This is the error, the distance between the current point and the true point. Then, because of this relation between the next error and the current error, E2 must be of the order of 0.0001. That is minus 2, minus 4. This is 10 minus 2. Becomes the square of the previous. And the third iteration, it becomes 10 minus 8, and so on. The error decreases very fast. We say that when it is square, we say that the convergence of the method is quadratic. Some research work using, but this is paper level, is more complex than Taylor series. Shows that Abou Kamel methods, I will note it like this, AKS. Abou Kamel method with Snyder modification, Illinois modification. The error, the next step, next iteration is of the order of EI, not square, but 1, 4, 4. And we call that is superlinear. The convergence is superlinear. Superlinear normally is 1.5, but is very close. So we call it the convergence is superlinear. So it's also very, very fast technique. But the cost now, as I said, don't compare only the performance, the rate of change of the error, but also compare the cost in Newton-Raphson method, Abou Kamel method, with Snyder modification, with or without. We have only one function to evaluate. But here you need f and the derivative, both. And the derivative could be actually more complex than the function, if we know it, we know how to calculate it. Sometimes we approximate it using a method called finite difference method. But whatever, you need to calculate. So the step here is at least twice slower, twice more expensive than, as I said, the step with Abou Kamel. With Abou Kamel is fast, while the step with Newton is slow. So don't only count the number of iterations due to the quadratic convergence, but also count the cost of each iteration. So it's important to know that the performance and the cost of each iteration. The fourth point important is the input. You have also to consider the input to your algorithm. This is general observation, not only in this topic. You could have a good method, but its input need preparation, is complex, etc. Here the input for the Newton-Raphson method and Abou Kamel with Snyder modification. Here you need IB, the interval, and the function. Here you need the point, start point, the function, and the derivative. So the input here is simpler than even the choice of the start is problematic. You could choose point that make the method divergent. So this is input. This is what you have to consider when you make a comparison, when you have several methods in any topic. Be sure that there are always pros and cons of any method. Nothing is perfect, but you have to do a compromise, a right compromise, by considering the performance, cost, and the input. Cost and the performance when the method is iterative, there is an iteration process, and the input of your algorithm or your method. That's it for. No, there is another point important. There is as any branch of mathematics, there is the foundation, then the advanced level, and then the paper level, the research level. There is a method, an advanced method, and I think it's still in research. There's still improvement in it, called Brandt's method. That's noted here. Called Brandt's method. Brandt's, due to Brandt. Brandt's method. In 1973. And he has actually based his technique on the research of another method. Another research worker, I think Decker. Sometimes it is called Decker-Brandt method. And what I have, I'm not sure about that, but it seems it is also in modification. Some research worker recently has improved it. But from what I know, in MATLAB, there is a function that relates to this topic that solve an equation, that look for a root of an equation called f0. Function is called f0. It starts with f. 0 means the root, and it is based on Brandt's method. It's an implementation of Brandt's method. Brandt's method is actually a combination of an open method, the secant method, and a bracketing method, a bisection method, but with more other details. It's not for a first course. It's more complicated. You can find a brief introduction to it in the work of Chapra, in the book Chapra and Kamel. But his paper level is not for beginners. So F0, you can use MATLAB. F0, you give the method, you give the function f, the interval AB, it needs an interval, and it returns the solution, XR, approximate solution, its image, and two structures, info, output, are two structures that contains extra information on the solution, like the number of iterations it took to the method to obtain the solution, extra information. You can check it in Octave or MATLAB. And with that, I think I have finished the chapter. You could, of course, try to go further as a mini project. You can, for example, study Newton method. It's an important method. You can study it like we have done with Abou Kamel. You study the method. You write a table dedicated to the method with a calculator and a pen, and then you try to implement it with an algorithm. You can also study the work on the research work paper level, but if you have good students, as a teacher, you can propose that as a mini project. Or if you are learning on your own, you are a student or an engineer or whatever, research worker, you can look for the rate of convergence of Abou Kamel method with the Snyder modification. It is purely theoretical, but it's important to study the rate of convergence of this method that we have used in this chapter. So that's it for this chapter. Next week, inshallah, we will begin our tutorials in Friday or Saturday. I will try Friday if possible. If not, then Saturday I will upload the first videos. There will be maybe 2 or 3 tutorials on this method. And see you there, inshallah. Peace.